All right, welcome. In this video, we are going to talk through some examples of Hess's Law. And let's just first review the rules regarding delta H values. And these are going to be important for applying to Hess's Law. So rule number one, if you multiply a chemical equation by a number, you're going to multiply delta H for the reaction by that same number. So for example, this reaction right here, let's say that the delta H for this reaction is, positive 10. If you were to double all these coefficients, the delta H would now be positive 20. If you reverse a reaction, you flip the sign. So again, this reaction, let's say it has a delta H value of positive 10 kilojoules. If you were to reverse this reaction and just flip around who's the reactants and products, then the delta H would be negative 10. And then if you add up two reactions, the delta H for the new reaction will be the sum of these two original delta H values. So again, if this one has a delta H of plus 10, and let's say this reaction has a delta H of negative 7, then you would add up these two values. So you have plus 10 and negative 7. The new reaction would have a delta H of plus 3 kilojoules. So these are the three rules that we're going to be applying in Hess's Law. And the goal of Hess's Law is we're going to be given a reaction like this one right here, and we're going to try and find the delta H of this reaction using this information that we're given. So I want to find a way to add up these three reactions. So you might be given 2 or 3 or maybe even 4. We want to try and add up these reactions to get this reaction up here. And along the way, we might need to reverse some reactions. We might need to multiply by a coefficient. So we might need to double things or maybe even cut something in half. Okay. So what I like to do is I'm going to focus on one of the molecules from this equation up here and see if I can get one of these equations on the bottom to kind of match up to this one. So I'm going to focus on the propane, that's C3H8. I noticed in this reaction, I have one molecule of C3H8 as a product. So I'm going to go down here and look, and I'm going to say, oh, look, this equation is the only one that has C3H8 in it, but this shows it as a reactant. So I'm going to want to flip this around. So I like to rewrite it. So 3CO2 plus 4H2O, you don't have to do this, but is C3H8 and 5O2. And so when I flip that around, the delta H reverses. Whoops. So this reaction has a negative 2,220. So the reverse reaction has positive 2,220 energy change. All right, now I'm going to focus on another substance. Let's take a look at hydrogen. So it looks like only one of these reactions contains hydrogen gas. That's this one right here. And it's on the correct side, it's on the left, but we need twice as many of them. So I'm going to double everything. Okay, so I'm going to have 4 hydrogens and 2 oxygens, making 4 waters. And then the delta H here, we're going to double it. So the sign stays the same, we're just doubling the value because we doubled the coefficients. And then our last one, I'll use a different color here. We're looking for 3 carbons. And it looks like this equation right here has carbon. It's on the left, so it's on the correct side. But it only has 1. We want 3 of them. So we're going to triple everything. This time I'm just going to write next to it. Okay, I'm going to triple everything here. And then I'm going to triple this value. So now if I add these 3 reactions here, if I add these 3 reactions together, I should get this reaction right up here. Notice how there are some oxygens, but they canceled out. Like we had 3 and 2 oxygens on the left and 5 on the right, so those all canceled out. And we have 4 waters on the left and 4 waters on the right, so those canceled out. So these all add up to get this equation right here. And I'll show you what this looks like here. So they all add up. So some CO2s cancel out, the H2Os cancel out, the oxygens canceled out, and we're just left with what we're looking for. And then when you add up these numbers right here, you get negative 103.8 kilojoules. Okay, so again, we applied all 3 principles here. If you change the coefficient, you multiply delta H by the same number. So we double these ones, so double delta H, triple these ones, triple delta H. if you reverse a reaction, you reverse the sign. So we applied that right here. And then when you add them up, you're going to get the delta H for the overall reaction. So we just applied all three of those principles that we were talking about right here. And that's how we do Hess's law. So there's not like an equation for Hess's law. It's just kind of mastering these three sets of principles and applying them to find the delta H of an unknown reaction. So let's look at one other example here. That one's pretty similar. Let's look at a different one. Okay, so let's look at this one. Practice number 3. Find delta H for this reaction right here. So I am going to, again, let's focus on one molecule at a time. So I want my reaction to have one NO2 on the right. And it looks like this reaction already has one NO2 on the right. So I am all set there. I'm not going to worry about that one. And then I want to have one NO on the left. This reaction has one NO on the left. So I'm all set there. So I want to keep this first reaction as is. Okay, let me maybe rewrite this one down here. So I've got NO plus O3 makes NO2 plus O2. So I'll leave that one as is. Okay, and the other thing that I want is I want some oxygen. So this is just atomic oxygen over there on the left. So only one of these reactions has oxygen in its atomic form here. That's this one. But this one has 2 oxygens instead of 1, and they're on the wrong side. So I want to reverse this reaction, and I want to cut everything in half. Okay, so I'm going to reverse it. So it becomes O2O makes O2 gas, and that's delta H is negative 495 kilojoules. That's the reverse. And then I'm going to cut everything in half. So I'm going to take 1/2 of 2 is just 1, and then 1/2, and then I'm going to take this number and multiply it by 1/2. All right. And then you might be wondering, well, what is the purpose of even having this equation right here? Well, notice that we have an O3 hanging out here that we don't want. Like my overall equation should not have an O3 in it. So the purpose of this equation is actually to kind of help us cancel out the O3. Same thing with the O2. We also have an O2 that we don't want really hanging around here. So let me use a different color pen for this one. If I want the O3 to cancel out, in this reaction it's on the left, I want it to be on the right in this equation. So I'm going to reverse this equation. So that will give me 3/2 of an O2 on the left and then 1 O3 on the right. So when I reverse that, the delta H is going to change in sign, 142.3. And then when I add them all up, hopefully I will get my reaction that I'm looking for here. So notice how I have an O3 on the left and an O3 on the right. So that cancels out. And then over here on the right, I have 1.5 oxygen molecules, O2. And then over on the left, I also have 1.5 O2s. So, phew, that canceled out as well. So when I add up all 3 of these reactions as written, I'm going to end up with the reaction that I was looking for. I think I have this written out. Okay. So I am going to end up the reaction I was looking for, which is I'm going to have an NO and an oxygen on the left, and I'm going to have an NO2 on the right. And I end up with negative 304.1 kilojoules. So this is the example. This is probably like the trickiest type of Hess's law example, where you have an equation here that's just being used to like cancel out the other something that's unwanted. But just kind of stick with your strategy. You're trying to, kind of like you're solving a puzzle here. You're trying to figure out a way to make these reactions add up to this reaction up here on the top. And yeah, I will go over, we can go over one more if you're curious. So you can stop the video if you're done, or if you want to keep going, we'll go over this one as well. Okay, so let's do this one too. So we've got these 3 equations, and we're going to use Hess's law to try and find delta H for this equation up here. All right, so I want to have 2 carbons on the left. And then in this reaction, this is the only one that contains solid carbon, but it only has 1 carbon, I want 2. So I'm going to keep it the same like direction, but I'm going to double everything. So this value here is going to double. All right. Now let's focus on something else. How about the C2H2? Okay, so this reaction contains C2H2, but it's on the wrong side. So I want to flip this reaction around. So I'm going to reverse it. So my products become reactants. So now it's 2CO2 and then H2O become C2H2 and 5 half O2. And when I flip that reaction around, it is going to change the sign. So it becomes positive 1299. All right. So I've got 2 down, 1 to go. So I got to look for my H2. So this equation has H2 on the left. So this one I actually don't have to change at all. I'm just going to leave it as is. And then now I am going to add up these 3 reactions right here. I'm ignoring the top one because that one became this one down here, if you're following along. Okay. So when I add these ones up, I'm going to notice that, look for things that cancel out. So it looks like I have 5 halves of an oxygen over here. So 5 halves, you can also think of that as being like 4 1/2, right? Got mixed fractions there. And it looks like, not 4 1/2. 2 1/2 is what I meant to say. Sorry. 2 1/2 oxygens. And over on the left, I also have 2 1/2 oxygens. So my oxygens cancel out. So my O2s cancel. It looks like, what else cancels? I've got 2 carbon dioxides on the left, 2 carbon dioxides on the right. So those cancel out. I've got a water on the left and a water on the right. So those cancel out. So what I'm left with when I add these up is 2 carbons and a hydrogen makes C2H2. And then if I add up these 3 delta H's, I'm going to get the delta H of my overall reaction. So this is why I like rewriting these equations. You don't necessarily have to do this, but I like rewriting them to make sure that they actually do add up to the reaction that I was aiming for. It's kind of a way to check your work. Okay. And so when I add these up, I get the delta H is 226. So overall, this reaction ends up being endothermic. All right, so those are 3 examples of Hess's law. So hopefully that helps you kind of see what this process looks like, and then send me a message if you have any questions.